So these are, this is called the 6.2, 6.1. Separable differential equations. Separable differential equations. So what makes them separable? What makes them differential equations? We'll talk about all these terms in a moment. And like I said, this is just barely scratching the surface of the possibilities of differential equations. There's a whole upper-level math class in college called differential equations, Diffie-Q, that talks about these kinds of equations and how to solve them and slope fields and amazing stuff. But we're just gonna do some basic ones here. So first of all, a differential equation is an equation where you have dy dx equals some formula, right? F of, well, I just to say some equation. Some stuff here, right? dy dx equals something. And so this dy dx is the slopes, right? This is all the slopes. Sometimes instead of dy dx, sometimes we say this is y prime. Is another way to I don't want too many questions, right? Sometimes this is y prime. dy dx y prime. Right? Same kind of thing. Same kind of thing. Right? So a differential equation describes the slopes of f, some function f of x. Okay? And creates a slope field, all of those things we talked about. Equation. Differential equation describes the slopes of f of x. Okay? And so what we want to find f of x equation. I should say the f of x, or an f of x equation. Find the general f of x equation. That means it has a plus c. From a differential equation, our goal is to find the general equation. Well, that's excellent to hear, Jennifer. Seems like it was a good time. I figured that's okay. Glad it was good news anyway. Bianca, welcome. Glad to have you. Make sure you say hello in the chat. We're taking some notes on differential equations. Again, the last topic that's going to be on our test on Thursday. So our goal from this differential equation, our goal is to find the general equation f(x) that has these slopes. That has these slopes. So to undo a derivative, dy dx, we do integration. We want to find the formula that has these slopes. What f of x equation, general f of x equation, means we're going to add c to it, has these kinds of slopes. And so to undo a derivative, to undo the dy dx, we have to do an integral. So let me show you how we're going to do this, why we call this separable differential equation. But anyway, so for example, let's take an example. If I have an equation, dy dx equals 3. This means that everywhere the slope of your derivative is 3 everywhere. So if you imagine the slope field of this, right, every point is going to have a slope of 3. Slope of 3, 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 slope of 3. Everywhere has a slope of 3. 3, 3, right? Everywhere's got a slope of 3. So the whole slope field is just a bunch of slopes of 3. What is the equation? What does the f of x look like that has these slopes? How do we undo this derivative? Well, the first thing we need to note is when we do an integral, when we do the integral, when we undo this, we need a dy on one side and dx on the other. In order to do the integral, every integral that we do has a dx. The integral, we need to do the integral of something, of a variable. We need to describe what we are taking the integral of. Which variable are we doing an integral of? Right? We need this dx in our integration. So to undo the integral, to undo the derivative, we need to have a dy on the one side. We're going to keep this dy piece on one side, and this dx piece, it's going to move to the other side of the equation. This dx, we're going to treat this like a variable. We're going to treat this dx like it is a variable. It is describing the the direction of our integration, the direction of our variable. So I'm going to multiply both sides by dx. What? Yeah, that's fine. I can do that. I'm allowed. I'm going to get dy equals 3 dx. So this is what we mean by separable differential equation. I separated the dy dx. Instead of saying this is one piece, I have made these into variables, and I've moved this to the other side. This is just describing, remember, this dy dx, all that it is doing is describing a rate of change. It's saying that the rate of change of y with respect to the x. How does y change, right? This is rise, dy, rise over run. Rise over run. It's a rate of change of y divided by the rate of change of x. It's like miles per gallon, or people per hour, right? Or bacteria per minute, right? How many bacteria per minute are there? It's some description of a rate. And so all I'm doing is moving the units to the other side. Instead of saying miles per hour, I'm keeping the miles on one side, and moving the hours to the other side. So now I have miles is some relationship compared to hours. How many miles I go has some relationship with the number of hours I've traveled. That's all this is describing. It's a description of a rate of change. And once we have separated these two variables, integrate both sides. What we're going to do is, like always in mathematics, what you do to one side of the equation, you do to the other side. And the rules of integration with x are the same rules of integration with y. When you integrate dy, well, let's look at this dx part first. integral of 3 dx. What's this going to be, everybody? When I do the integral of 3 dx, what equation is this going to give me when I do the integral of 3 dx? What is that going to make? Someone in the chat, remember our integration rules. What's the integral of 3 dx? Great, Jennifer, exactly, 3x, right? When you do integrals, you add the x back. So this is going to be 3x, and then we're going to say, plus c. We've got to add the c here. 3x plus c. So when I did the integral of dx, I got the x back, right? Integral of dx, you can imagine this integral of dx leads us to have an x. Well, what would happen if I did the integral of dy? This is, remember, a 1 dy, 1 dy. So what do you think the integral of dy is, everybody? If the dx gave me the x, integral of dy, this gives me a y. Right? Integral of dy gives me the y back. Just like an integral of dx. So what we're saying is what direction we're doing the integral of. We're doing the integral of the y variable here, and we're doing the integral of the x variable here. That's why every integral has to have a d whatever, dx, dr, dy, dm, dt, whatever your variable is, you're doing the integral of that variable, and you get that variable back. And so this is the equation of f of x. This is our equation. F of x. So it's 3x plus c. And you see we can have, right, we can have all kinds of different equations. We can have 3x plus 0 goes through the middle there. This is 3x plus 0 plus 0. This is, we can go up to 2. We can have 3x plus 2, 3x plus 2, or 3x minus 5, right? We have all these different equations of 3x plus 0, plus 2, all these different equations we can have depending on our starting value. Which of these points do we want to be touching? Our graph will go through those different values, and that will be a different c value. So this is how we solve these differential equations. You move the dx to the other side, do the integral of both sides, get your equation. Okay? Questions about that? So we do our integral, we separate our dy dx, get our integral. So let's try one more. Oopsies. Let's try another. Solve for f of x if dy dx equals x plus 2. dy dx equals x plus 2. So here, we're going to do the same thing here that we did above. We have to move the dx to the side over here with the x's, right? We have to move this dx to this side over here because the dx goes with the x's. Right? Dx goes with the x's. If there were any y's in this equation, the dy would go with the y's. So the dx goes with the x's, dy goes with the y's. So move the dx and dy, move x's and dx together. Move the x's and the dx's together. And if there's any y's, move the y's and the dy's together. I'm going to multiply both sides by dx, multiply by dx on both sides, and I'm going to get dy equals x plus 2 dx. Notice that I put the x plus 2 into parentheses because I am multiplying the entire x plus 2 piece, right? When I multiply the whole side by dx, I'm multiplying the entire x plus 2 piece by dx. So I move the x's and the dx's together, the y's and the dy's together, and then I integrate both sides. Integrate both sides. Integral, integral. So it's nothing really new that we've done. We've done integrals before. We know how to do the integral solving. It's just we're doing a little bit of algebra beforehand. We do a little bit of rearranging beforehand. Yeah? So the integral of dy is y. Integral of x plus 2 dx. What's this x plus 2 dx? What is the integral of this one going to be? In the chat, somebody tell me, what is this integral? Thank you, Perry. So very good. X squared over 2. X squared, because we bring the x back and then we have to divide by 2, plus 2x plus c. Don't forget your c, everybody. Make sure you're adding your c because we can have lots of different equations, right? And that's it. There is your equation of f of x. Describing the functions that would travel along this x plus 2. If we made a slope field of that, it would look like a bunch of parabolas, right? Be going down, then up, or up, then down, right? Whatever the equations look like. So those are easy. Yeah? Let's go on this a little harder. Let's do a little bit more challenging. What if it has a y? dy dx equals, let's say we have cosine of x over y. Ooh. dy dx of cosine x over y. What do I do here? Oh, it's not that hard. There are harder ones. Really, you know what a real hard one is? dy dx equals x plus y. This one is hard. But it's so easy. Just add what's the problem? Yeah, try doing the integral of this. Tricky. This one, easy. This one's very easy. Yeah, multiply, right? We got to separate the x's and y's. Put the y with the dy and the x with the dx. So I'm going to multiply both sides by y, put the y over here with the dy, and then multiply both sides by dx, multiply both sides by dx, put the dx over there. So I swap their positions, right? I move the y with the dy, move the x with the dx. So what am I going to get? Y dy equals cosine x dx. Right, move the y with the y, move the x with the x. And now, integrate both sides. What do I get here, everybody? Let's do the cosine x side first. What's the integral of cosine? Who remembers? Thank you very much. Sine, yes, right? The integral of cosine is what thing makes a derivative of cosine? The derivative of sine is cosine. So this is sine x. We'll add the c in a little bit. What about the integral of y dy? Well, even though it has a y, it follows the same rules as x would. So if I have a y, just like we did, right? Just like we did up here, right? When we did the integral of this x piece, we got x squared over 2, right? Because we brought the x back in, increased the exponent by 1, Integral, you add exponent by 1, derivative, you subtract. So my integral of y dy is going to be y squared over 2. Right? Now I know this is plus c out here, but this plus c we're going to kind of deal with later. Deal with later. Because first, we have to simplify to a y equals equation. This formula is correct. This is the absolutely, this equation is the solution to this dy dx. Problem is, I want to make it a y equals equation. Right? I want to get a function here. And to get a function, I need to remove the y, move all the things over, get the y by itself. So we're going to do a little solving. Right? Simplify to y equals. So what can I do? Well, multiply both sides by 2. Multiply both sides by 2. Cancel the 2 there. Y squared equals 2 sine of x. And you see what I do, what I mean by we'll deal with the c later. Because really what I'm doing here is, okay, well, I'm multiplying, okay, multiply the c by 2 also. But some random constant times 2 is still a random constant. So I'm just going to kind of leave the c over here. We'll just kind of deal with the c at the very end. That c we're just kind of going to leave until the very end and then just tack it on. Because everything we do to the c is just making it some other random number. So it doesn't really matter what we're doing. We're making it a random number. That's fine. But the rearranging, we have to do the rearranging to the equation. So multiply both sides by 2, and then y squared, got a square root. And again, square root of c doesn't really matter. It's just going to be a c, right? So this is going to be y equals square root of 2 sine of x plus c. There's your equation. I guess we could say plus minus here. Might be important. Right, simplify to y equals. So a little bit of algebra, and then we get our equation. Questions, concerns, worries? All right. So what we do is we multiply both sides by the y, rearrange these things, get some stuff figured out, get our answers all coordinated. There is one trick that we need to know, however. One trick. One complicated situation that arises with these dy dx problems. One complication. And this is important, little complication that arises. What if I say dy dx equals x times y? Some situations, you're going to have this complication here. One complication we have to deal with. Complication. And this complication involves E and ln. We're going to have to use the natural log and the exponential in some situations doing these differential equations. And let me show you what I mean. Here's an example. dy dx equals x times y. When I rearrange this one, can anyone see the problem here? Multiply by dx, both sides, that's fine. Multiply by dx, both sides, right? Cancel the dx. But when I simplify the y side, I have to divide by y or multiply by 1 over y, right? So I'm going to get 1 over y dy equals x dx. Right? This is my complication here. This fraction of my 1 over x is my complication. It's not that complicated. It's just one more thing to remember how to do to these problems. So we're going to do the same thing. We're going to integrate both sides. We just got to keep going, right? And if we remember, the integral of 1 over x x dx is the ln, the natural log of x. Something you have to remember with integration rules. They love to throw this into problems. And by they, I mean me, and by me, I mean Thursday. Love to throw this into equations. That the natural log is 1 over x, the integral of 1 over x is natural log. This kind of connection here. So when we solve this, when we do the integral of 1 over y, this is going to be ln of y equals x squared over 2 plus c. What? Okay. So the integral of 1 over y is ln of y, and the integral of x squared is x is x squared over 2, right, plus c. So now to solve this, to simplify and cancel ln, cancel the ln. What is the opposite of ln? Anybody remember? I mean, we didn't really cover this a lot, but the natural log has an opposite of e to the power of both sides. E and ln are opposites. E to the power and ln of natural log, these cancel each other, just like a square and a square root. Ln and e are like a square and a square root. They all cancel each other out. So to get my ln y, to get this y out of the ln here, to cancel the ln, I have to do e to the power of both sides. E to the ln of y equals e to the power of x squared over 2 plus c. And e and ln cancel out. Really, I should have just done this beforehand. Let me just do this here. E and ln cancel out. Let me just put the y on this side. Makes my life easier. This is just a y. One more thing we have to do. E to the a plus b is e to the a times e to the b. One more thing we have to do. We have to deal with this c part. Remember how last time I said with the square root and the sine, all of that stuff, we just dealt with it and put it on tacked it on the end at the very end? No problem. Because when you square root a random number, you still get a random number. When you exponentiate, however, it becomes a different situation, because now the c is an exponent, and that really changes things. So we're going to use this little rule here, that e to the power of a plus b, I can separate those two pieces into a multiplication. Remember? It's like if you say, right, x to the power of 3 times x to the power of 5 is x to the power of 8, because you combine the exponents together, right? You add the exponents. When you multiply, the exponents get added. Same thing we're doing, but in reverse now. We're backing it up. We have the addition. We're going to split it into two multiplications. So this is y equals e to the x squared over 2 e to the c. And this e to the c is just a random constant. Sometimes they call it c sub e. So we're going to say y equals c sub e, e to the x squared over 2. So instead of adding a constant in front, we have our constant being multiplied in the front. Constant is multiplied in the front. So instead of plus c in the end here, we have this c being multiplied in the front. This is where we have our initial condition here. Really, you don't really need the e either. You can just call it c, but sometimes you'll see a little e written down here. You can have it or not. I don't really care either way. But I want to let you know that sometimes they do have a little e written down there in front of the constant. Or just c. So instead of having the plus c in the end with this exponential situation, we have this exponential with a c in front. So it's just slightly different situation. And again, you'll have to deal with that using ln. ln e to the power of ln cancels out. Okay? Questions about this process? So this one complication is when you have your 1 over y, or 1 over x, whenever you have a 1 over x or 1 over y, or x or y to the negative first power, they give you e and ln's, right? That's going to be involving e and ln. You have to deal with that situation. Maybe e to the power of both sides. Cancel stuff out. Put this c in front. All right, last thing. Now that we know how to do this, now that we know how to solve these equations, we want to find a particular solution. One more thing. So these are all general solutions. Find a particular solution. I have 5 minutes, so I got to do this fast. Solution with an initial condition. Initial condition. Condition. So what we're going to do is we're going to do the same thing. Find f of x if f of 0 equals 1 for dy dx equals x squared plus 2x. Do I like that? Let's say 3x squared plus 2x. Yeah, I like that. So we're going to rearrange this equation. Dx on both sides, dx on both sides. I don't need to move any y's around. That's great. dy equals 3x squared plus 2x dx. Integrate both sides. We're going to get y equals, what's this equation? Someone in the chat, plug this in. What's the integral of 3x plus 2x dx? That should be easy. I know it's going to be x cubed over 3 times 3. Yeah, the 3 and the 3 cancel out, right? So these 3's cancel out. So that's x cubed. And then this one is just going to be x squared over 2, right? So that's x squared. Plus c. Yes, thank you. Y equals x cubed plus x squared plus c. So this is the general solution. Right? To find c, to find C, plug in x and y. Right? We had x and y listed here. X and y, right? So now I have an initial condition. I know that the location of this point is 0, 1. I know the graph passes through this location. So I know that, like if I had my chart, right? If I had my graphing chart, I would have some kind of, crazy lines everywhere here. I know that 0, 1, 0, 1 right here, I know that my graph, whatever graph I draw, has to go through that point. That's what this is saying. 0, 1 is a solution of my function f. This is the function f of x. And for this particular function, instead of the general equation, I want to know this specific equation. And so I give you a specific point that it's located at, and we use that specific point as like a pin to stick the graph into one spot. Right? We have this general field where the graph can be kind of anywhere, and then we say, no, here. This is where I want the graph. Pin it to a spot, tack it down, and everything else has to come around from that spot. Right? That's our initial condition. From that sticking point, from that tack, everything else becomes a general formula. So we plug in our x and y. We got our y is 1, so that's 1 equals, my x's are all 0, 0 plus, oh, goodness gracious, 0, and that's a 0, 0 cubed plus 0 squared plus c. In this case, c is equal to 1. That was easy. So my equation is y equals, oh goodness gracious, y equals x cubed plus x squared plus 1. This is my particular solution. Right, this is my particular solution here. Where I found a value for c, I have a specific graph now located on my equation. And you can do this with any of the equations, right? Plug in your x and y. Once you get the general equation, plug in your x and y, get your specific one. So these are what we're going to do. Solve these differential equations by taking an integral of both sides, finding a y. Sometimes you have the y is a little more complicated. Sometimes you have to do like an ln or e. Sometimes you have to square root your y's, right? And then you can, for any of these, you can find your initial condition. Let me underline here. Whoopsies, underline here. So that's what your assignment's going to be, your homework this evening, to try some of these out. There's 12 questions. I posted a thing to Schoology. Let me show you all that.